Texas Lutheran University.
And then Madison Berger. They're going to talk about their experiences being interns with the U.S. Department of Agriculture. So Carly spent some quality time in Beltsville, Maryland, and Madison was in Fargo, North Dakota. So we're going to hear about what their adventures were this summer, because I think they really embraced their adventures shoes this summer. Carly, you ready?
Yeah, sure. I'll go.
Can we turn off that?
There's one.
Well, this is
Is that okay still? Yeah, great. Okay. Hello. I worked with the USDA in Beltsville, Maryland. I was in specifically the Crop Systems and Global Change Laboratory, which sounds a lot cooler than it actually is. It was just a lot of dirt mostly. So I did a couple projects, the first one being like the main one, the rice project. I found out later that they made this project for me because they thought I was really interested in arsenic and rice, so they did this. But either way, so it was like a pot experiment, and we mostly looked at cadmium. So we took soil that had a high level of arsenic, and then we took different levels of cadmium and added it to the soil. So we had 3 different concentrations of cadmium. And then we also did 4 different water contents. We had like a rain-fed, like as needed, a 40% moisture content, 60% moisture content, and a flooded. And so overall we had 48 pots, and they each had 4 replicates for the each total experiment. So I got to prepare the soil for the rice, which was a lot of fun. And so we wanted the pH of the soil to be about 5 to 5.5, and this is because this allows the plant to absorb the metals, because it's available to them at that pH, because a higher pH would make the metals bind to other things and not be available. So I got to use calcium carbonate and magnesium carbonate to lower the pH to get that perfect level. And so we took the soil that had cadmium in it and mixed it to make 2.5 parts per million, 10 parts per million levels of cadmium in the soil. So those were the 3 different concentrations. And we had 3 kilograms per pot. And we added nitrogen, phosphorus, and potassium fertilizer that was made and then added to the soil. And the soil was watered and mixed around for 2 weeks, so it was all like well mixed in the pots. So then we got to plant the rice later. And so we germinated this rice, and then the ones that like started to like bust out a little bit, we planted 5 per pot. And the water treatments didn't start until 5 to 6 weeks after planting. And in this video, I don't know if you can tell, but me and my partner are weighing the pots, because we wanted to make sure like we knew exactly how much water the pots were getting, because each pot gets a probe in it, and the probe determines the water volume content in the soil. And so we used how much water we added and lost over time and compared that with what the probe was telling us, so we could figure out how much water we needed to add for the 40% versus the 60% and as needed, and like where that ranged. And later I found out that the probes are like $1,000 each, and we had 48 of them. So after that, I was a little nervous to handle them, but we did this because we did so much controlling this, because they've never been used in pots before. They're usually meant for fields, and so this is how we tried to adjust for that. And so this was like one of the last times I saw the rice, and I got a recent update saying the rice is doing well. But other than that, I'm not sure how it's doing. I hope it's doing great. And so the other projects I worked on were involving soil. And so there was one about carbon sequestration, which basically means the soil holding carbon, which is a good thing because we don't want carbon dioxide in the atmosphere. It's better to have it in the soil. And so that we looked at soils that had a history of adding biosolids, which is like a compost of some kind, a history of adding biosolids from somewhere in the 1900s, like from 1950 to 1980s range. If there was some added, we analyzed the soil there. And so we had soil samples from Maryland, Virginia, and Illinois. And we took a top soil layer and then a subsoil layer from all the different locations. And I think we had a total of like 200-ish samples of that. And then the other project was another soil project that took garden samples from the Baltimore area, and we analyzed it for lead and cadmium. And so all these dirt samples, so I had like 500 samples of soil, so a lot. And so I did a lot of stuff with it. This video is me taking the pH of samples. So anyway, to prep the soil, they all had to be dried, crushed, and then sieved to be like all like uniform so we could analyze them better. And then like put into sample bags. And then for pH, you take a 1-to-1 soil to distilled water, and then you can take the pH of it. And we also took the electrical conductivity of the soil. We took the electrical conductivity, which is a 1-to-2 ratio of the soil and the water. That just determines the how conductive the soil is. And then we also did a carbon analysis on all the soils, which we just grinded them up, and I just grinded them up, and I think there's a carbon analyzer that did that, but the technician took care of that. And then the other two, I did Aqua Regia and the DTPA. And so in Aqua Regia, this measures the total metals in the soil. And so we used 15 grams of the soil sample, and we used a mixture of 3-to-1 hydrochloric acid and nitric acid mixture to take off the metals of the soil. And so we did that, added it, then heated it, then let it evaporate, then added it again, heated it, then cooled it, and then we filtered it, and then we brought it up to 50 milliliters with 1 normal nitric acid. And then once that was done, then we got to analyze it by the flame AA. We were going to do the ICP, but it wasn't working that day. And so this is the one time I got to use like an instrument at the USD lab, which was really cool. And I think this video turned out kind of nice. And so this measured total metals. And then the other method was the DTPA, which is this measures the metals that are available in the soil. And so the solution contains DTPA, which is diethylene triamine pentaacetate, calcium chloride, and then triethylenol-amine. So there's me making it, and it had a pH of 7.3. It was very specific. And then they were, so 15 grams of that with 30 milliliters of the solution were shaken for 2 hours. It's a very like timed thing. It had to be exactly 2 hours and then immediately filtered. And I don't have a video for the shaking, but just imagine it just like shaking back and forth. And then the samples are refrigerated, and they can be kept for several months. So I had lots of them in the refrigerator because I did not get to analyze them. And so I don't have a lot of data for you, but it was very cool. But I can tell you about my experience in Beltsville, Maryland. More like every single weekend, I think, me and my friends went to DC. I think I went to DC every single week. And so it was really cool. I met not thousands of people, but lots of people. And so the picture on the left is like the people I like most hung out with. I think all of them are from A&M Kingsville. And they're all like, they're all like animal people, because like the USD does animal stuff and plant stuff. But it was cool to like get to know them and like stuff, and they all wanted to do things with me. But it was really cool. So I met like in the USDA, there's so many people from around the world. Like I met, like the people I worked with specifically, a guy was from Jamaica, there was someone from Ethiopia, there was someone from the Philippines, there was someone from Cameroon, which is a country in Africa. And so it was just like cool. I was like surrounded by like diversity, and it was really cool to meet all these people, and they all liked me, and I got to do cool things. I went to like a Pride festival, saw Miley Cyrus. I was like 100 feet away from Miley Cyrus. It was pretty cool. I got to go to a Game of Thrones themed bar, which was like super cool. And then also that picture on the very right is 4th of July. They have this massive fireworks show over the reflection pool, and it was like the best. I was like, once you see one fireworks show, like you're seeing them all. But this was really cool. Like they were doing like geometric 3D shaped fireworks, like cubes and smiley faces. It was cool, I promise. So I hope, and that's pretty much it. So I really enjoyed my experience. So I'd like to thank Dr. Codley and Dr. Green for my mentors up there. They love their soil and stuff. So really appreciate them. And then Dr. Bray for being the one to present this opportunity, like, hey, do you want to do this? And I'm like, yeah. And then USDA NIFA for providing me the opportunity to go, and then family and friends for supporting me. Yes, that's it. Any questions?
For Carly?
Great.
Dr. Davis has a question.
Oh, do you have a question?
What's the DTPA doing with the metals?
I don't really know.
You took inorganic, didn't you?
I did.
You should know.
I should know, should I? Do you want me to guess?
Yeah, oh, sure. That's why I asked. Yeah.
Um,
Do you remember what the structure of DTPA is?
I just looked at it. It's a very organic-y looking molecule with lots of ends. It looked kind of like straight though. Is it kind of binds?
Well, that's a picture somebody put in a book.
Oh,
But
okay.
when you put a metal, what's it going to do
It's
to the
gonna
metal?
bind around
Yeah,
it.
what do we call that? That's a fancy word.
There probably is a fancy
Starts with
word.
a C.
Smorgasbord?
Exactly. Metal. Yeah.
Circling.
Chelate.
Oh, chelate. Yeah.
That's why it's you're doing the available metals with that, right? So
Yeah.
it's basically caging the metal.
Gotcha.
So it pulls it out. I
Great.
have one other one, unless anybody else.
Yes.
Yeah.
All right, so
Oh,
dealing
no.
with equilibrium
Okay.
now. Would you consider going to work at the USDA? if the
Yes,
job was available?
I would. I really liked it, and just looking at my mentors, they're having a great time. Like Dr. Codling is he's like my favorite person ever. He's like the Jamaican who's like, hey man, yeah man. He was friends with everyone, and yeah, I would definitely
So what else
consider.
did you grow?
It's the weed. That's why he's friends with everybody.
No, literally, one of our greenhouses was next to a greenhouse that was caged off. He's like, that's where they grow the good stuff, or something like that. He said. So it was fun. So yeah, I would definitely consider working for the USDA.
The pay's good.
Yeah, it is.
Mhm.
Are they looking for PhDs?
Because you can actually look up their salaries because it's a federal job. Not that I did that.
They do, yes.
They-
Nothing bad.
okay.
Anybody else got another one?
Yes.
Well, you said you added calcium carbonate and magnesium carbonate to adjust the pH.
Yeah.
Which way did you adjust the pH? I want to make sure I heard that right.
Which way?
What do carbonates do to pH? Do they raise it or lower it?
Don't they lower it?
That's why I asked.
I thought
What's
it
a carbonate? When you put a carbonate in solution, what happens to the pH?
doesn't it make carbonic acid, or does it not?
Well, no. Sort of.
It needs hydrogen.
Yeah, yeah.
right?
Yeah. Okay. So it takes
What's the
away.
Like if I took, and by the way, the analytical students will know this, should know this after they did all their titrations, right? What was the pH of the titration, the calcium carbonate titration you guys did, or sodium carbonate, same difference? Anybody remember when you started? Who's the analytical? Here, I can pick.
Ramiro.
You don't remember?
It was basic. It was
was
in
like
the
a-
10, 11 range.
Yeah, exactly. Carbonates are basic.
Okay, so we brought up the pH.
Yeah, I just wanted to make sure you, yeah.
Well, and
You may have misspoke that.
Wondering,
Might have.
so environmental people, why does carbonate seem like a strange choice? If you're trying to get to a pH of 5.5, what would be a better buffer system? Because what does carbonate
Aluminum.
typically buffer to? You want to use what?
Aluminium.
Aluminium? Okay. Because remember the buffers for carbonate only system are gonna be more like pH 8 for soil. But your soil's probably got a lot of stuff going on in it too, so.
It did. Yeah.
Soil's complicated.
Good soil. Yeah. Lots of stuff in
Okay.
it.
All right, we'll leave it alone.
Whew, okay.
Oh, wait, one more question. Would you recommend going to Beltsville for another internship if somebody had the opportunity?
I would recommend it for people who have a free summer next summer.
what do you mean?
Good job.
Is
No,
this
it's
the
the
clicky?
That's the quickest.
Okay.
And it's a laser pointer too, so.
All right, so as Dr. Bray said, my name is Madison Berger, and my internship was in Fargo, North Dakota. So this is the building that I spent 7-ish weeks of my life in. It's located on the North Dakota State University campus, but it's a totally separate unit. So you've got USDA, you've got North Dakota State University. But they do collaborate on some projects with students just for the experience. So in Fargo, they have different units. In the USDA, they've got insect genetics, sunflower and plant botany, cereal science, sugar beet and potato research, but I got to work in the animal metabolism unit, and I was specifically, one project was working with food safety, and the other one was antibody related, so I'm going to talk to you about both those projects. So first off, the antibody project, it was optimizing characteristics of an antibody that the USDA found, and they created this antigen, injected it into a rabbit, and then the antibody was created. And I got to test the best coding concentrations, primary antibody concentrations, secondary antibody concentrations when you're doing an ELISA assay. And I also got, more importantly, I contributed the cross-reactivity check. And then for the second project, which is more commonly known as the sheep project, that's actually what I'm doing my senior sem over, so I'm going to talk kind of briefly on what I did, but not too in-depth because I'd like to save that juicy stuff for the spring. But I got to do a urine collection, lateral flow test, and ELISA assay of the zilpaterol in sheep tissue. So previous work, this is talking about the antibody project. Scientists at the USDA, specifically Dr. Shelver, which was my research head scientist of my unit or whatever, she created this antigen called pramomycin BS3-BSA. They injected it into rabbits, that was their test subject at the time, and then the rabbit actually produced antibodies to protect against this chemical, and they were able to extract those antibodies, and now they're trying to test the sensitivity of it and what it can do, what it can yield off, and such like that. So this is what they created. They took pramomycin, they complexed it with KLH, which is like a big protein, just to make it more visible to the antibody. And then they also complexed it with BS3, which is bovine serum albumin. And so they injected that into the rabbit, and then it produced those antibodies. So I was using an ELISA assay technique. It's an 8-hour process. It took me the full day, and it was super tedious. There's 4 different types: direct, indirect, sandwich, and competitive. I used an indirect assay, meaning I was adding primary and secondary antibodies. And these assays are used to detect for peptides, proteins, hormones, and I was using it to detect for antibodies. So this is just a big picture overview of what an indirect ELISA is. You start by coating your plate with the coding antigen, which was the pramomycin BS3-BSA. You incubate that, and then you coat it again with a primary antibody, which is what they were able to find from the rabbit. And then you add a secondary antibody, which is an anti-rabbit antibody. And then from there you add something that will change the color of the reaction, so you can put it in like a UV vis and detect where that inhibition is happening. So this is it, laid out step by step. I figured I should go into detail about this. So the very first step was the coating step. So as you can see on the top right, that is what you call, it's your plate, and each of those little circles is a well. So it's like a centimeter deep, and you were able to put liquid into it. So for the first step, you took your pramomycin BS3-BSA, and you combined it with a buffer, and then you applied that to the plate, and then you would incubate it for 2 hours. And during that incubation time, the antigen was attaching to the surface of the well, and then you were able to rinse it off completely. So you would rinse your plate as you pulled it out of the incubator, and that would get rid of any liquid on it, so it was completely dry. But you still had your antigen stuck to the plate, basically. And then the next step was the blocking, and you would add that primary antibody to see if it could detect the antigen that we had just added, and then the blocking would block sites where no activity was happening and nothing bound to it. because that took away from the sensitivity that the instrument could read, and it improved your results basically. And then from there you'd incubate it again for an hour and a half, and then wash the plate again in the plate washer, which is that bottom right image. You would just put it in and it would go through and rinse every single hole. So you had to wait for that. Then you'd wash it, and then the next step was, it was another blocking step, and you would add a secondary antibody, which was, they called it anti-rabbit. Not really sure what it does, but it's a thing. And you'd incubate that again, and then you would wash it. And then you add a color indicator, so you could put it in the UV vis, because a clear liquid the UV vis wouldn't pick up. And that's what you see on the left. It turned everything blue, and it gave that nice little color pattern. You'd incubate that again, and then you would add acid, which would stop everything going on the plate. There were no more reactions occurring, and it turned it yellow. And then from there, you would put it in the plate reader, which is on the bottom there. And it's just like a UV vis, and it would just go column by column and shine the light through it and give you your results. So a lot of what I had done was just practice the ELISA assay and the technique, and towards like the last 2 weeks, they were rushing to try and get results from me, so they wanted me to do a cross-reactivity check. So they took chemicals that were in the same family as pyramomycin, so it was the aminoglycosides. They took chemicals in that same family, and we tested them to see if the antibody could detect them like they detected the pyramomycin. So the percents read like how well the antibody was inhibiting these chemicals. So neomycin, you can see it was a 75% inhibition, but you can kind of tell by the structure of the pyramomycin on the left and the structure of neomycin that they're very similar, so the antibody was able to pick that up. Gentamicin, you go down in an aromatic ring, but it still did have some inhibition, and then as it goes on, the rest of them weren't, it wasn't picking it up. And so those were the main results they got from me out of all of that, but yeah, it was cool. So the second project, the sheep project, we contaminated food with zolpadrol, which zolpadrol is a beta agonist, and in humans it acts as a bronchodilator, so it's going to shrink those muscles in your airway, so you'll find it in asthma medications like inhalers. But in animals, you add it to their feed and it'll improve their metabolical processes, which is what I plan on looking into for my senior sem and the science behind that. But basically, it gets your animal ready for market quicker, and you can send your meat off and get the money for it. So as of right now, the US has 2 beta agonists that it approves, and that's ractopamine, which the USDA has done a lot of research on, and then zolpadrol. They now approve, but there's not a lot of research on that, so that's one of the reasons why they're conducting this project right now. But approximately 160 countries ban the use of these beta agonists, which is bad because like China and Russia are in that 160 countries, and we do a lot of trading with them. So we have to make sure before we send our meat off to these countries that they don't contain any more of this beta agonist. Otherwise, they'll send us our shipment back, and we lose money from that. So the purpose of this project, yes, that's a nice little sheep. There's very little data, like I said, published about zolpadrol, and accidental exposures do happen. There's been some cases of racehorses. They find racehorses with zolpadrol in their system, and that's not good. And then also with show animals. So we were determining what concentrations are detectable and how to detect them. So a general overview of the project, there were 4 separate trials. When I got to the USDA, they were just starting the project, and I believe it just finished this month. So I don't really have that many results for you. I can just kind of tell you what I did. But there were 4 separate trials. They lasted about 3 weeks each. We had 4 different treatment groups. There was a high, medium, low dose, and then a 3-day withdrawal. And then we also had control sheep. So we would bring new sheep in. We always had 2 control sheep at once. Like the control sheep never changed throughout the whole experiment. And then we had new sheep coming in every 3 weeks. So we brought the sheep in. They were allowed to get familiar with their environment. They were allowed 7 days. They were just fed regular feed that wasn't contaminated. And then on the 7th day, we dosed their feed. And then we would collect urine every other day and test it to see if there was zolpadrol already in it. And then we slaughtered them and harvested them after 13 days of feeding them with contaminated feed, and then currently what they're working on is determining the concentrations of zolpadrol in them. So for the urine collection, you would literally take a little Velcro belt and you would wrap it around their midsection, and there was a little plastic beaker cup that you'd put over. And that's, we needed about like 5 to 10 mils, so once you got that much, you could take it off of them. They initially tried a method where you, because there's been a little research published on it, where you close off their airways for a minute and then they'll pee. And we tried that, and as you can imagine, they didn't like that, and it was more hassle than it was worse. So we just put the cups on and let them do their thing for a little while, and then they would pee. So I didn't actually have to put a belt on any of them, but I assisted, of course. So one of the on-the-spot methods that we used to test whether there was zolpadrol in the urine was a lateral flow test, and this was just a qualitative test, so it would tell you yes or it would tell you no. And these are the strips you would use. You add urine onto the sample pad, which is at the very top, and it would flow down the strip. The very top strip is just, it's there, and if it's not there, that means the strip is no good, so it was just kind of a check method. The second line, if there is a red line that's distinct, that means there's no zolpadrol in the urine. But if the line is faint, that means there is zolpadrol in their system. So it was just kind of a yes or no check. And the USDA, they actually made these strips. They're not going to actually sell them because I did ask because they could make money from that. But they actually handmade these strips. I got to help make them. So for the slaughter and harvest, I didn't have to help with this either, but I assisted. The organs we kept for analysis were the kidney, liver, lungs, and muscle tissue. The lungs specifically, because like in humans, they act as bronchodilators, so that's where you'll find the zolpadrol or whatever. So we kept the kidney, liver, lungs, and muscle tissue, and on harvest day, they would dice this up, separate it into tubes, and then they would put it right in the freezer. And then from there, they had my research partner and I unthaw them, put them in a blender with some dry ice. You grind it up, and it's like the consistency of a milkshake, but it uniforms your sample, and it's easier to run data quickly if it's in that form. So we got the privilege of making meat milkshakes. And then, so more of the fun adventures. I got to canoe and kayak for the very first time, and it was actually on the Red River, so that was kind of cool. I rode my bike everywhere, to the grocery store and whatnot, and I rode to work, so that was a really cool experience. And I got to hop on over to Minnesota, because I was only like a 30-minute bike ride from there. Minnesota. And then, yeah, there's a lot of cool scenery. Absolutely loved my experience. Would go back again if I could. And for my acknowledgments, I'd like to thank Dr. Bray for the opportunity and lining up the grant, Dr. Mike Grusak, who helped arrange the grant, my mentors at USDA, specifically Dr. Shelver, Dr. Smith, and Amy, who was the lab tech that I worked with 24/7, and then Tyler Huff, he was another intern that was there at the same time as me. And then USDA NIFA for funding this experience, and my family and my friends. Any questions? Please make questions.
Questions for Madison? About meat milkshakes or anything?
There's a sheep shake.
Sheep shake.
No questions.
Yes, sir.
Yeah, so the context you used to elicit the antibody response, so it was made out of a small molecule, the
Paramomycin, yes.
LH,
Yes.
and BSA,
Yes.
all three together.
Yes.
So you have all three linked together.
Yes, sir.
You actually made it in the lab, synthesized in the lab, or?
It was pre-made when I got there,
Mhm.
so, but yes, the lab tech and Dr. Shelver, they both made it. I don't know how they did it. That was before my time, but.
I have a follow-up question on the same topic, because you have BSA is kind of a relatively big protein, and ovalbumin, which is a small protein,
Yes.
has been known by itself, okay, to elicit an immune response. So is there any particular reason why your mentor chose to link the BSA with the biggest, the KLH, which is even bigger than with the other molecule?
I think they were just trying to get the antibody to detect it. I think they were just trying to make it obvious for it to.
So to get a stronger response.
Yes.
Other questions? Dr. Maloney?
Can you go to the slide with the paramecium? That's what I want to say paramecium. What's that?
This one.
No, with the analogs that you were testing.
Oh. Oh boy. These.
Yeah, with the gentamicin, you said that it was aromatic.
Oh gosh. They're not aromatic, are they?
Well, what's an aromatic ring? What's
It's
the most famous one?
benzene.
Is there benzene there?
No.
That's generally what they are.
Okay.
Would you like to change your grading?
Yeah, I'm gonna go with that. Between that and those pants, it's gotta change.
Anything else? No. Okay, solid.
All right.
For more information, please visit tlu.edu.